morning, everyone, and good afternoon and good evening for the folks in Europe. Welcome to another edition of the Finite Element Seminar at Lawrence Livermore. Today is my great pleasure to introduce Xevi Roca. He is the director of the Geometry and Meshing Simulation Group at the Barcelona Supercomputing Center, and he's really one of the pioneers of high-order curved meshings for practical application. Certainly has been an inspiration for our work in this area. So it's really an honor and a great pleasure to have you, Xevi. So thanks for agreeing and for coming to talk here today. The talk has a lot of interesting things for us. It's focused on aeronautic applications, but it has all the meshes and borders, preconditioning, all sorts of cool things. So thank you, Xevi. And with that,
thank you very much, Zanio, for the introduction. It's actually really my pleasure to be here in this seminar series. I really like what you're doing with this seminar, so I'm glad to give this talk for you. And I will talk mainly about our contributions to help to enable high-order methods for high-fidelity simulation, mainly for aeronautic applications. And something that the community is doing, and also we are trying to do, is to combine geometrical, numerical, and physical aspects of these high-order methods to obtain better results. So if you can pass to the next slide. So I'm going to cover what I said in the abstract, but I'm going to change it a little bit. So I will put a lot of focus on the last things that we are doing. Actually, the current work that we are doing at the BSc, together with Guillermo Aparicio and Eloy Ruiz, and also our collaboration with Martí Circuns and Josep de la Puente from the Wave Phenomena team. Can you pass to the next slide? Thank you, Zanio. And I would like also to acknowledge our previous collaborations and other research groups, because without their work, this presentation would not be possible. And we got a lot of inspiration of these works of other people. And I want to highlight also that, as you know, we have a lot of intersections of interest, and we were learning a lot of your work, Ketan, Vladimir, and Zanio. So thank you very much for your invitation and your work. And next slide, please. Okay, so the main motivation is that we are really interested to help to enable analysis of future aviation designs for aerodynamic applications mainly, but now also for electromagnetics. And the problem is that the current industrial softwares that are used for doing these simulations use low-order methods, both for geometry and simulation. And this is critical because without high-order methods, some analysis might neglect key interactions between the design features. So this is an example to illustrate this. This is the fuel-efficient Aurora D8 design by MIT and NASA. And here what you can see, I cannot show with the cursor, but I will do it with my words. You see a wider body to accommodate more people, and you also can see that the shape of the airframe, it's not the standard shape. And the reason is because the shape is also trying to provide lift to this design. And what you can see here is that the propulsion systems are not on the wings, they are on the back part of the aircraft. And actually what's going on is that these propulsion systems are exploiting the low velocity air that comes from the top part of the aircraft. So these designs are going to exploit this kind of key interactions. So can you go to the next slide, please? So I'm going to, because I want to focus on the things that we are doing now, and I want to go in more detail, I will give a quick overview of the things that we were doing before. So basically, what we do in the team is we try to devise high-order methods for HPC simulation. We are in the Barcelona Supercomputing Center, we have this supercomputer, and we want to use it. And actually what we is that the people has good methods to do new things. And we always are worried about unprecedented geometrical, numerical, and physical accuracy. We were mainly focused in this part of the geometrical accuracy, but also in numerical aspects of high-order methods. And nowadays, we are working also in terms of physical accuracy. And always taking into account that we want to be efficient. And I'm going just to overview three basic research results. These are the last thesis of the group. We have the work of Guillem Belda, where we have 40 refinement. Actually, he also got an ND refinement for simplicial meshes and structured meshes. Then we have the work of Guillermo Aparicio for curved adaptation that overlaps a lot with the work that you are doing here at FEM with at LLNL. Okay, and basically here what Guillermo was doing is an optimization-based framework where we were using the distortion measure of Patrick knob. We adapted to take into account the target metrics. And this is in the geometric part of the methods, because what you're doing is try to accommodate the mesh to the geometry of your physical features. But there's something more going on here. If you want to do this kind of optimizations, you need really good nonlinear solvers. And Guillermo also proposed a nonlinear solver that was specific for this kind of problems. Also, again, for the numeric side, we were working on optimal interpolation. This is the thesis of Albert Jimenez Ramos. And he did this work on obtaining points that try to minimize their suboptimal points, because you don't have you don't know what's the minimum, but they are points that minimize the Lebesgue constant. They are really suitable for high-order methods, mainly for interpolation. And actually, he also did some work on geometrical aspects of high-order methods. He was using the points that he proposed to interpolate surrogate geometries. And on the right-hand side, we have what we would say applied research. We start on the left-hand side, and in this left-hand side, we actually do this basic research that we try to push forward to higher technology readiness levels. And I will give a quick overview of that work that was mainly pushed by Aloy Ruiz and myself the last years. Okay, can you pass the next slide? I was trying to do it, and it was not working. Okay, thank you, Zani. Okay, so you can see that I'm talking a lot about geometrical aspects, numerical aspects, physical aspects, and this is something that we did a long time ago. This is something that actually was pushing Jaime Peraire, and we were really interested in the accurate prediction of the transition from laminar to turbulent flow. Here you have in the bottom part an airfoil with a free stream coming from the left. The free stream goes from the left to the right, and on the first part of the flow, you have a really well-ordered flow. It's a laminar flow that is attached to the flying surfaces. Then you have a transition region where small perturbations grow exponentially until the point that you get this nonlinear behavior, this turbulent behavior with these eddies and fully chaotic flow. It's really important to be able to predict where the transition happens if you want to obtain the right quantities of interest, such as the leaf coefficient and the drag coefficient. And to do it so, we were combining an entropy stable high-order HDC method, a hybridizable discontinuous Galerkin method, on curved meshes. And the combination of these ingredients for high-order, we were able to obtain, actually this was the results of the thesis of Pablo Fernandez, we were able to obtain really accurate prediction of the transition region, so also of the quantities of interest. Can you go to the next slide? Okay, so for the rest of the talk, I'm just going to mention our previous works because I decided, as I said before, to give more details on the preliminary results that we are working now. So for the geometry, I'm going to give just a quick overview of the work that Aloy Ruiz and myself we did in high-fidelity curved meshing, mainly for CFD, and then I will present these preliminary results in the numerical and physical aspects. The first one is going to be low-order preconditioning for DZ. So this is on the numerical side of the solvers. And for the physical part, I will talk about preserving the semi-discrete Poisson structure of a discontinuous Galerkin method for computational electromagnetics. Next slide, please. So let's go with this part, the high-fidelity curve meshing, which is a geometrical aspect. Next slide. Okay, and here the problem is that If you want to analyze the aerodynamic performance of an aviation design, you will need larger scale meshes that feature really high fidelity. And the problem is that current methodologies maybe do not guarantee that high fidelity. And this, again, is critical. Without high fidelity meshes, there are not high fidelity analysis. And our solution is quite unique because what we do is we allow that the mesh floats around the geometry. We put tight tolerances on the approximation of the geometry, and also we put tight tolerances on the minimization of the distortion that is based on the Patrick-Knopf distortion. And we do it at larger scale in parallel and trying to guarantee this high fidelity. Really smooth meshes, really optimized meshes with as much quality as we can get and really accurate because they approximate the CAD until the limit of reaching the 10 to the minus 6, which is the limit of the current CADs. And this is showing that it will allow to enable high fidelity analysis that agree with the experiments. On the left-hand side, you have a detail of a curved mesh. It's actually a coarse mesh, but you can get pretty good results with this mesh running a solution of polynomial degree 4 of the NASA High-Leaf Common Research Model. And on the right-hand side, you have two pictures. One that is experimental data. So you put an aircraft at the scale in the wind tunnel. You put oil on the surfaces. It's actually fluorescent oil. And then you take pictures of the straight lines of this oil flow with fluorescent lights. And you try to get a simulation that matches the experimental data. So what happens? Some people at NASA does the experiments in the wind tunnel. Some people generate the curved meshes, like Eloy Ruiz did for this example. And some other teams are using those meshes to run the simulations. There are different teams doing the meshing challenge, other teams, they do the simulation challenge. And CJ Wang was using our meshes and other meshes, and he was able, using our meshes, to reproduce the qualitative features of the experimental data. So this is a good verification of what we are doing could be helpful in the long term, even for the industry. Next slide, please. And this is just, these are some pictures because we're going to see less pictures in the next slide. So this is going to be nice to see this, but it's actually a small history of that we were doing. On the top left part, we have these pictures. These are results of my PhD thesis with Josep Serrate. Then Abel Gargallo, in his thesis, obtained results for volume and CAD optimization of a point-wise distortion measure. We were also working with Heyman Chaurasia in his thesis for moving meshes together with Jaime Peraire and Pedro of Poisson. And later, the first work as a postdoc of Eloy Ruiz, together with Josep Serrate, was to do these curved meshes, where the meshes were sliding on top of the CAD. And in 2017, Eloy and myself, we started to think new ways to do the approach. So we were exploiting his idea of just optimizing the volume and not caring about the quality at the surface. It's going to be a surrogate of the good quality in the volume. And also I had an idea, which was, let's not do the sliding the points on the surfaces, allow them to float around of the CAD. And this is actually what we are doing for the high-leaf prediction workshop in the 4th, the 5th, and the 6th edition. And this is the end, in some manner, the end of the story. So we are mainly tweaking and not researching about this subject. Next slide. So after these pictures, we will go with a little bit of weak forms. So let's go with numerics. We are going to consider low-order preconditioning for DG. Next slide. And it is well known that high-order methods have a lot of advantages, but also they come with some disadvantages, mainly the storage and conditioning problems. So let us consider that we want to solve a Poisson problem with Dirichlet conditions at the boundary equal to 0. This is the work that Guillermo Aparicio is leading, together with Eloy Ruiz, and supervised by Eloy Ruiz and myself. And basically, the idea is that we want to precondition these problems because we want to skip these problems of storage and conditioning. It is well known, everybody knows that the number of non-zeros per row for high-coordinate methods scale with p to the d. And for instance, for symmetric interior penalty, which is a kind of a discontinuous Galerkin method, the condition number scales with p to the fourth and times 1 over the square of the mesh size, as Pazner and Kolev demonstrated. So next slide, please. And luckily, Pazner, Kolev, and Dorman, they found a solution for Legendre Gauss-Lobato meshes with cubes. And the idea was the next one. Why not to consider the points of a Legendre Gauss-Lobato discretization of high order of polynomial degree plus 1, I just use them to generate a submesh inside each cube that is also composed by by cubes. And this mesh is bounded by the LZLP plus 1 points. And they were able to obtain a spectrally equivalent matrix, low order matrix, that if you use it as a preconditioner, the number of preconditioned iterations is it's constant under H and P refinement. So the idea is, okay, let's just store this low order matrix for preconditioning, and let's use matrix-free actions of the high-order mesh in the outer iterations of the Krylov solver. And in this manner, they got affordable storage because the number of non-zeros per row of the low-order matrix is independent of the degree P. Next slide. But we are really interested in simplices because we are dealing with these geometries, and the capabilities that we have is give me a CD, let's generate a linear mesh, and let's carve that, linear mesh. Simplices are known to have automatic linear mesh generators. This is not the case for hexaedra, but of course there are a lot of hexaedra can also handle complex geometry, but you will need more human intervention to obtain the results. You have less automation. Actually, there's not an automatic algorithm to do it so. So in our case, we're interested in simplices. So we were learning for the work of Pazner, Kolev, and Dorman, and we wanted to do something similar, but for simplices. So there are some differences. First, we care also about equidistributed points, not only about clustered points. And we want symmetric points in the simplices. And we want a preconditioner not only for symmetric interior penalty, also for local DG, which is the method that we would like to use in our applications. So our idea is the next one. It's a really similar idea. But here, instead of using subcubes, we are going to use subpolytopes, that is, polygons in 2D and polyhedra in 3D, that are dual to the high-order points, the nodal points. So in circles, in this plot, you can see the nodal points for a high-order space. You can see in blue the boundaries of the triangles of the mesh. And actually, these boundaries correspond to the skeleton of this mesh, DH. And then we have this subpolygonal mesh in each element, which is dual to each one of the nodal points. This polygonal mesh is depicted in gray in this plot, and we have two main regions. The region that intersects the skeleton of the original high-order mesh, and the region that is inside of the original high-order elements. Next slide, please. So how we can get this subpolygonal mesh to fulfill this idea? So basically what we do is we consider a master equilateral element in 2D and 3D, and then we get these sub-elements by clipping a Voronoi tessellation. And we are just illustrating this for polynomial degree 6. In the first row, you have the results in 2D for triangles. And the second row, you have the results for tetrahedra in 3D. And in the columns, you have on the left-hand side, the equidistributed points. And on the right-hand side, you have clustered points. So what's going on here? For P6, in 2D, you have 28 nodal points. And if you take, for instance, the central point, this point is going to be coupled with itself and all the other points when you look the equations at the elemental level. So 1 against 28. Accounting for itself. Okay, But what happens if I solve a low order problem in the subpolygonal mesh? Let's take a look to the dual mesh of the central point. This dual mesh is exactly the orange region in the center of the triangle. And this hexagon is surrounded by 6 hexagons. And the adjacency, the coupling, is going to be with those elements that share a face with this element. So now you're going to have the coupling with yourself and also with your neighbor, so 1 to 7. So in 2D, you go from 1 to 28 to 1 to 7. Let's do the same in 3D. You go from all a nodal point coupled with all the nodal points, so 1 against 84, and for the cells, what you will have is more or less in mean, because you have different regions on the tetrahedron. You will have like 24 polyhedra around the central polyhedra. So this is what's going on: 1 against 84 to 1 against 25. And this is how you reduce the number of non-zeros in your system. Next slide, please. Okay, so let's reproduce, for simplices, something similar to the work of Pasner, Kolev, and Dorman. And here the idea is that we consider VP, the broken space of polynomial of degree P greater than 0, on a simplicial mesh TH with a skeleton EH. And we're going to seek a solution U in this high-order space, VP, broken space, such that for all the test functions, the next bilinear form is equal to 0. And here, some of you will be used to linear forms and weak forms and so on, and some of you are not going to be you are not working that much on that. But what I only need from you is that you take a look that on the first term on the left, which is a volume term because it's an integral on all the elements of the mesh, you have gradients of u and gradients of v. In the second term, you have gradients of u. It's an integral on the skeleton of the mesh because it's an integral on EH. And the third term also have a gradient of b. These terms would disappear if p is equal to 0. Here, the curly braces are for the average and the brackets are for the jam. And sigma p is just the corresponding penalty to make the method stable and penalizing the discontinuities of the solution u. Next slide, please. Okay, but we are saying we want a low order. We want a low order matrix that comes from a low order method. So why not to use a broken space of constants on the subpolytopic mesh T0 with a skeleton E0? And here what we are going to seek is a U in the constant space, the broken constant space, such that for all the test functions, the bilinear form is equal to 0. And when, as we said before, there's only one remaining term for the symmetric interior penalty, which is the skeleton term that goes with penalty, because the other ones have the gradients. And here is where is relevant what I said before, that there are two main regions of the subpolygonal mesh. Okay, the skeleton of that subpolygonal mesh has two regions: the one that intersects with the original skeleton in blue of the high-order mesh, and the region that is inside the elements of the high-order mesh. And if you do that, you can separate the integral in these two pieces. The piece that doesn't touch the skeleton of the high-order mesh, which is the inner part, and the part that intersects with the skeleton of the original high-order mesh. Next slide, please. Okay, and in our preliminary results, we are considering a penalty term sigma 0 such that we have only one term that we could decompose it in two regions, and integrals in two regions. And in the first region, what we have to do is that this term approximates the integral in the volume of the high-order mesh for the gradient of u and the gradient of b. But now we are not integrating in a volume. We are integrating in the interior of the high-order elements, but only on the skeleton. So we are going to consider a weight w such that the integral resembles the integral of the volume, and at the same time we are going to approximate the gradient of u and the gradient of v in the following manner. the jump of u over the jump of x, and the jump of x is actually the difference between the coordinates of adjacent polygons, subpolygons, okay? It's going to approximate the blue term, the gradient of u. And the green term is going to, the jump of v over the jump of x is going to approximate the green term on the right-hand side, the gradient of v on the volume integral. And now for the other term, the things are more easy because the only thing that we need is that integrating in all the subelements of the skeleton of the subpolygonal mesh that intersect with the high-order mesh, you get the same result as you integrate on the skeleton of the high-order mesh with sigma p. And actually what we do is that the contributions of all of them is like they behave as the sigma p. Okay, this is for symmetric interior penalty, and there are some similarities with the work of Pasner, Zanio, and Dorman, but we were interested also for LDG, and here the difference is that we will need to do something similar with the numerical fluxes that appear in the DG formulation. And the DG formulation just arises from the following first-order system. You have a vectorial variable q that is equal to the gradient of u in omega. Then you have the physical equation minus the divergence of this new variable q is equal to the source term. And we have again Dirichlet conditions equal to 0 at the boundary of the mesh. And when you do the DG, the discretization for local DG, you will obtain two equations, one for the q and physics. And in this equation, you will have numerical fluxes that you have to tune to try to emulate with low order the behavior of the high order terms. Next slide, please. And let's go for initial results. So for doing so, we are going to consider a manufactured solution in the unit square such that the solution is polychromatic. This is actually a benchmark proposed by Kolev and collaborators in a seed report. So we decided to use the same benchmark because it stresses the iterative solver. And we are going to get results for symmetric interior penalty, but also for local DG on symmetrical simplices with equidistributed and warped points. So on the left-hand side, you have this picture where in the x-axis, you have in logarithmic scale the mesh size h. On the y-axis, you have the number of preconditioned iterations in logarithmic scale. And you will see two main groups of curves in the plot. When you go from the right to the left, you are refining the mesh. You start from one element per side of the unit square until you reach 128 elements per side of the unit square. So from coarse to fine when we go from the right to the left. And what you can see is that when you don't precondition, that is the preconditioner is actually the identity, which is the same as you are not using a preconditioner. For all the methods, what you get is that the number of iterations grow with the refinement of the mesh. And this makes sense. And we put a maximum number of iterations. These are results that Guillermo got. We'll put a maximum number of iterations of 1,000. And you can see this region where you can see how the number of iterations grow linearly in the log scale. What's going on? Remember, the condition number is the reciprocal of h, of the square of the mesh size h. And then you have all the other preconditioned problems with the low order problem that they get a constant number of iterations when you refine the mesh, and this number is between the hundreds and the tens. Good. This is actually what you want, and this is what we learned from the paper of Pasner and Zanio and Dorman. And we were able to reproduce this part with simplices. Let's see the results under p-refinement. Now, we are not going to consider that we don't precondition. We use the non-preconditioned solutions to illustrate what happens when you don't precondition it, but we don't care about that now. And now we are going to use the same manufactured solution that is polychromatic in the unit square. And on the x-axis, you have the polynomial degree that goes from 1 to 10. So you're going to do p-refinement. And on the y-axis, you have the number of preconditioned iterations in logarithmic scale. So what's going on? When higher is the polynomial degree, higher is the number of iterations. It's not that bad because you go from below the tens, around the tens, to between the hundreds and the tens. Okay, but it's not flat as the previous one. Of course, if in your applications you have a fixed P, which sometimes happens at least in aerodynamics and also in electromagnetics, maybe P4, P5, P6, that you are getting really good results, really, really low dispersion and dissipation results, you are fine. But nevertheless, we think, is there a way that we can improve our penalty terms or our numerical fluxes to get better results? And this is a tricky question. We don't know the answer, but it's true that we don't have something that you have when you use cubes. So in their work, Pasner, Zanio, and Dorman, what they exploit is that a cube, an LGL cube, a Legendre Gauss-Lobato cube, is the tensorial product of 1D LGL segments. And for 1D LGL segments, you have really nice properties of interpolation and extrapolation, and also of norm equivalences that they can use in terms of the tensorial product. This is not the same for simplices, so we have to see if we are able to find a way to improve these results on P refinement. Next slide. Of course, this is what I said, we would like to improve the P refinement, but we are happy for some applications where you have a fixed P or with the things that we get. Guillermo is polishing and reviewing the proof of the spectral equivalence for symmetric interior penalty and local DG. So we are going to send a first draft soon. And we were talking about the preconditioned conjugate gradients iterations, okay? But what's also important is how many iterations you need to compute the action of the inverse of the low-order matrix. We tried different preconditioners, and here you are seeing a plot for the accumulated iterations of algebraic multigrid. So in the x-axis, you have in logarithmic scale the mesh size. Again, when you go from the right to the left, you are refining the mesh. And in the y-axis, you have the accumulated iterations in logarithmic scale. And you can see that as you refine, the number of iterations go from below the hundreds to between the hundreds and the thousands. But you have an outlier, which is actually the symmetric interior penalty for warped points. And we think that what's going on here is that the algebraic multigrid is not going really well because you have a grading of the mesh size. This subpolytopic mesh has clustering of the sizes, and we think that doesn't work really well with AMG. So we will see if we can improve the number of accumulated iterations just by tuning AMG or using a different AMG or even programming our own preconditioners. Next slide. Yes. Okay, so the summary is that we have this idea for low-order preconditioning for simplices, where we consider subpolytodes that come from a master mesh, okay, that are dual to the nodal points. In this manner, we get the preconditioning matrix of low order. We do it for symmetric interior penalty and local DG on simplices, for equidistributed and warped points. And of course, we get affordable storage because the number of non-zeros for the low order problem is independent of the polynomial degree. This is what they also saw here at the LLNL. And the number of preconditioned iterations is constant under H refinement. Under P refinement, the number of iterations mildly grows. Next slide, please. So let's go with the physical aspects of high-order methods, and we are going to focus in electromagnetics. And what we want is to obtain a DG method that preserves the semi-discrete Poisson structure of the Maxwell equations. This is the work for the PhD thesis, part of the work for the PhD thesis of Martí Circots. Next slide. So here in our department, we're interested to get capabilities for electromagnetic observability. We want to analyze for future aviation designs the radar fingerprint. So basically the idea is that you have a radar that emits electromagnetic waves. These waves are scattered by the aircrafts, And our waiver takes part of the scattered waves. And the problem is that when you go to large scale and you want high fidelity analysis, some standard methods do not scale that well. And without scalable and accurate methods, the design and analysis cycles are too slow. So next slide. So our solution is to get a capability in the department that is numerically and physically accurate to be able to do this large scale analysis using a high order solver. And the benefits that we expect in the long term is that we can enable fast and high fidelity analysis that agree with the observability benchmarks. So this is something that these are results that Eloy Ruiz got in a prototype for complex geometry. This is actually the NASA Common Research Model. Use it as a perfect electric conductor. And you can see the scattered electric field on the left-hand side. And these results were obtained in 4 hours using 14,000 processors, CPUs, not GPUs, because this is the prototype. And Josep de la Puente is actually pushing a demonstrator that is going to run also on GPUs. And on the right-hand side, you are going to see what the engineers are really interested. What they want is, in the x-axis, they have the angle. You have an incoming wave that is planar from the front of the aircraft. And for the different angles, you want to say, in this case, for the horizontal plane, you want to see the ratio of the incoming of the scattered signal against the incoming signal at infinity in decibels, so which is actually a logarithmic scale. So when higher is the number, more visible is the object. When lower is the number, less visible is the object. This is the quantity of interest for the engineers. Next slide. So motivated to get these capabilities, we proposed it to Martí to start his work on the thesis. And we wanted to promote not only the numerical accuracy, also the physical accuracy of the method that we want to implement. And to explain what we are doing, I'm going to show here a simplified set of Maxwell equations and a simplified problem for the sake of clarity. So we're not going to consider currents and charges. We are going to have E and H for the electric and magnetic fields. Epsilon and mu are the material and the electric and magnetic material parameters. Omega is going to be a periodic domain. We don't want boundary conditions that makes the explanation more difficult. And the final time is going to be denoted by T. And we're going to consider initial conditions for the electric displacement field and the magnetic flux density that are divergence-free. In our work, we consider boundary conditions and also currents. Next slide. Okay, so this is the standard DG form, starting from the Maxwell equations for this case. And what's important is that on the left-hand side, you have the dynamics of the electric and magnetic, the electric displacement and the magnetic flux. And on the right-hand side, you have two terms: volume term, which is an integral on the full mesh, on the volume mesh, and also an integral part on the skeleton of the mesh, which in this case is going to be for each element, the boundary of each element. What you want is that this weak form fulfill for all the test functions in BP and for a solution EH that is in the broken space of polynomials of degree P. You have to set the numerical fluxes, here denoted by the asterisk. And if you do an additional integration by parts after doing the Galerkin projection and the first integration by parts, you get the strong weak form proposed by Heskaven and Warburton. Next slide. And it is well known that when you combine this semi-discrete DG method with a high-ordered explicit time integration, for instance, explicit range kata of order P+1, you get really low dispersion and dissipation for these kind of problems, and they are really well suited for distributed parallelization on CPUs and GPUs. However, this discretization does not preserve the Poisson structure of Maxwell equations, and Sanchez and collaborators state. And actually, in other words, this is actually well known in the computational electromagnetics community. And what happens is that for long time simulations, the conserved quantities might drift, for instance, the energy. Next slide. Okay, so there's a solution that was studied by Sanchez, Du, and Guyen, Coburn, and Pereire and is that you take your standard DG, they do it also for other methods, let's focus on a standard DG, and if you use center fluxes or alternative fluxes, the semi-discrete standard DG is equivalent to a semi-discrete Poisson system. And you shouldn't care about this Poisson system. Here I'm just plotting how it goes, and basically is a way to describe anti-symmetric things in physics to ensure that you have conserved quantities. So the idea is that you're going to have derivatives in time of functionals, in this case a functional FV and a functional FH, which are actually the coordinate functionals, and then you're going to have a non-canonical discrete bracket, Poisson bracket, here denoted with curly braces and an H, that is going to take two functionals. It's going to use the functional derivatives of these functionals. They are going to combine them in such a manner that is anti-symmetric, and you are able to resemble the dynamics of the electromagnetic equations. What happens when you use this discrete DG form? That the discrete energy and the electric and magnetic charge follow a conservation law. And for other quantities, what happens is that in long integration periods, the quantities remain remarkably no drifting. Next slide. And how they prove that this semi-discrete form preserves the Poisson structure? So they start from this weak form for a standard DG. They parameterize the fluxes for DG and the numerical traces for the Poisson bracket, and they manipulate the volume skeleton terms through equivalences until they reach the semi-discrete Poisson system. However, the proof for a standard DG is inherently intricate. And we were thinking, okay, is there a way to obtain a different DG method, some kind of DG method in semi-discrete form that also is you can transform to a semi-discrete Poisson system, but that is closer than the standard DG? And this is what we proposed to Martí for his thesis, for part of his thesis. Next slide. And we put two requirements. Okay, to facilitate the preservation proof, we required a weak form that is closer to the Poisson system. This is what we want. But we cannot forget, okay, that, okay, you could say, okay, let's implement directly the discrete form, okay, and some people does similar things to that, but we wanted to exploit our existing structures of DG codes to be able to implement a new method. So we put another requirement. We want that the weak form presents and modified test functions. And when we did this, we obtained the following semi-discrete form. So for electric field E and magnetic field H in the broken polynomial spaces of the degree P, we want to obtain a solution such that fulfills this weak form for all the test functions B and W in the same spaces. Here, the curly braces are averages and the brackets are jumps. And what you can see is that on the right-hand side, you have an integral on the skeleton of the mesh TH, boundary of TH, on both equations on the right-hand side. In one, you have the jump of H accompanied by the test function B, and the test function appears without any modification. The same for the W in the equation below. And this is good for implementation purposes. Next slide, please. What's the path that we use doing transformations, equivalent transformations to get the Poisson structure? And the first thing is that for that weak form, there's a term which is I cannot sign with a cursor, but it's the curl of H times the test function B in the volume of in the mesh volume. Okay, and you can see that you have an alternate sign between the top equation and the equivalent term in the lower equation, plus against a minus. And now I have an H that goes with a W, and both are accompanied by the curl, and then you have a V that goes with an E. So you have a pairing, and you have an alternate sign. So actually, this is anti-symmetric. But then you have two skeleton terms, one in blue and one in green. And here you are not going to be able to see any anti-symmetry directly because you have a minus, and then H and W play different roles and B and E play different roles. Okay, but this DG form that we are proposing can be transformed in fewer steps than a standard DG into a skew symmetric system. And the idea is that if you manipulate the expressions, what happens is that you can remove the half of the jam of H and you can convert it to a numerical trace on the test function V. The other thing what that happens is that if you want to remove the average on E, on the top equations in green, in the green term in the bottom system of equations, you will see that E appears with a hat, and then the outer product doesn't go with E, it goes with W in the green term in the bottom part of the low set of equations. You have minus against plus, H paired with W, B paired with E. Good. And this is just explanation for center fluxes on periodic boundaries, but we do it for alternative fluxes also and general boundary conditions in our work. Next slide, please. Just for closing the proof, you already have this skew symmetric system that actually just to evaluate the semi-discrete system in Poisson form. Forget about the Poisson system. I'm just saying that if you evaluate these functionals and their functional derivatives and you put them on the Poisson bracket and you do the time derivatives, you are going to obtain the system that we have above. So they are equivalent. So that's all. We are able to resemble in fewer equivalent steps something that is a Poisson system. Next slide, please. If you implement this weak form, this new standard, this new DG method, the first thing that you have to check is that you implemented well and that you are getting a high-order method. So let's do a space-time convergence study. And to do it, so we consider a cavity mode on a vacuum square for a perfect electric conductor boundary. On the bottom part, you see a little illustration of this standing wave for polynomial degree 4. And actually what you're seeing in color is the y component of the magnetic field. In a space, we are going to have a mesh of size h. We are going to use our semi-discrete Poisson preserving DG of polynomial degree p. And in time, we are going to have a resolution of delta t. We are going to have a final number of periods equal to 100. And for the time discretization, we are going to use an explicit symplectic partitioned range cut method of order p plus 1. This is the other ingredient. We are using a symplectic high-order method for trying not to break the semi-discrete Poisson structure of the problem. Next slide. Actually trying to exploit it. And what we see is that the electric field converges with order p plus 1 and the magnetic field converges with order p. Okay, what's going on? And this makes sense because actually the magnetic field is related with the magnetic flux, which is actually at the same time the curl of the vector potential. So it's a derived quantity of the vector potential. You're losing one order of convergence, and that's the reason because the magnetic field converges in that manner. In rows, in groups of rows, we have polynomial degrees p equal 1, 2, and 4, the first column. In the second column, we have the mesh size. The third column, we have the delta t. And what we do for the convergence test is to divide the mesh size by 2. Then we plot the errors, but what we care is about the order. And what you can see is that you get this p plus 1 and this p. The only one that you get something a little bit weird is for p4 that you get 3.99, but this is actually a 4, which is what you expect for the magnetic field. Next slide. Okay. But we do all of this because we want to have some discrete quantities that follow conservation law. And to do a test, why not to consider a traveling planar wave on a rectangle, a periodic rectangle? So what goes out from the right goes in from the left of the rectangle. Here you're seeing in colors the z component of the electric field for polynomial degree 3. In space, we use our semi-discrete Poisson preserving DG. And in time, we use for 300 periods a explicit symplectic partitioned range cut method of order p plus 1. Next slide. And what you get is an analysis of this discrete energy error and the discrete linear momentum error. These are results that Martí got actually a long time ago. And with the results, you have on the left-hand side, you have in the x-axis, you have the time. On the vertical axis, you have the error of the Hamiltonian, which in this case is actually the energy, in logarithmic scale for polynomial degree 1, 2, and 4 in blue, orange, and green, respectively. And you get closer and closer to 0, actually below 10 to the minus 4 for P4. And you see that these lines are flat. And this makes sense because you have a discrete conservation law actually for the energy, the magnetic charge, and the electric charge. But what's going on for the discrete linear momentum? This is a quantity that for this discrete form doesn't follow a strict discrete conservation law, but what's going on is that it remains not drifting for long time periods. On the x-axis, you have 300 time periods. On the y-axis, you have the error of the linear momentum in logarithmic scale. And you are using, here we are using blue, orange, and green for P equals 1, 2, and 4, like in the other plot. And you can see that the lines, the orange line and green lines are flat, but they are weird. They have like some kind of thickness. And if you look the blue one, it seems that drift a little bit, and it's also thick. What's going on? What's going on is that we have oscillations of the error, and that the amplitude of these oscillations is smaller when higher is the polynomial degree. And the other thing that we see is that when higher is the polynomial degree, smaller is the error. Okay, this is just an illustration of conservation and no drifting for this kind of methods. So next slide. So we have derived a new DG method preserving the semi-discrete Poisson structure. And to do it so, we imposed two requirements. We wanted that it was easy to implement using the structure of an existing DG code, and that the proof of the preservation of the Poisson structure was easy. Accordingly, the price that you pay is that your weak form doesn't come directly from a Galerkin projection of the Maxwell equations. This is the price that you pay, but actually in the continuum, they are equivalent. We use explicit symplectic partition and Runge-Kutta methods of order P plus 1, and we are able to obtain a convergence of order P plus 1 for the electric field of an order P for H. And remember that this is because the magnetic flux is a derived quantity of the vector potential. Next slide. Here, what we get is that doing the same as Sanchez and collaborators, but in a different manner, of course, we are going to have a discrete energy and electric and magnetic charge that follow a conservation law, but the discrete version of other quantities is not going to follow conservation law, the discrete conservation law, but at least is going to remain no drifting for long time periods. The current work of Martí in this subject is to get 3D results. He's writing a code for this. I have to say that the results of Guillermo Aparicio, he wrote all the code. In this case, Martí also wrote the code. He's working in 3D. And he's also working in benchmarks on dissipation, dispersion, and reversibility. And here, Josep de la Puente is teaching a lot to us about these subjects because he's an expert in wave phenomena. And finally, the next steps is to incorporate these methods in our electromagnetic observability capabilities. Next slide. Concluding remarks. Next slide. Okay, so we have seen detail of low-order preconditioning for DG on simplices with symmetric points. And the idea is that you generate a subpolytopic mesh on a reference element that you map to the physical space. And when you do that, you get a low-order preconditioner that allows you to get a constant number of outer iterations of conjugate gradients under H refinement, and the number of iterations mildly grows under P refinement. Next slide. We have also seen a new DG method that tries to preserve the semi-discrete Poisson structure. It has applications for electromagnetics. And to do it, we imposed that it was closer to the Poisson structure, to the Poisson system, not that it was easily implementable using existing DG codes. And we have some quantities of entities that follow a discrete conservation law, and at least the ones that doesn't follow these discrete conservation laws do not drift significantly for long time periods. Next slide. So summarizing, we are in the group, we are devising computational methods to help to enable high fidelity analysis of aviation designs, both for electromagnetics and computational and aerodynamics. And to do it so, we are combining solutions for geometrical, numerical, and physical challenges of high-order methods. And we are doing this because we want that our methods help to analyze future aviation designs. So thank you very much for your time, and sorry about the issues with sharing the screen.
This is Jerome Solberg. That was a really interesting talk. I wanted to ask, just because I know that sometimes this is an issue with the DG codes for the electromagnetics, how it does with the divergence-free condition
Okay.
for
So,
B.
okay. So actually, here what you need is that the initial field is divergence free, and then you have a part of numerical preservation, but also this is actually corresponds to the divergence of the magnetic flux. So we have to check that. It behaves like the Heshaven and Warburton thing, but I'm not sure if it behaves better and worse. I cannot say that. Okay?
Yeah. Okay, cool. Because you know that a lot of times you deal with that by construction, but here because you don't have you have a discontinuity across the edges, it could possibly go there's nothing necessarily controlling it. So thank you so much.
Yes, you're absolutely right. But I think what's going on is that there's a no drifting quantity, but I'm not able to tell you when, for instance, the Heshaven and Warburton DG method and this one, they crosses in fidelity for the divergence free thing. I'm not sure. Because this one is going to is going to approximate a shadow Hamiltonian and is going to oscillate. Actually, I don't know. We didn't test on how many periods the things get worse or better for which one of the methods.
Great. Thank you so much. It was really interesting though. And
Thank you.
yep.
Thank you, Jerome. So I can mention something while we're waiting for the folks. I thought the law order preconditioner is super interesting. We are also interested in simplices. I mean, most of our applications are on tensor product elements here, but we do have some on simplices, and obviously meshing is much better there. So this idea of the dual mesh, and yeah, that's kind of cool. Very cool. We also don't know how to make it optimal in P. So mild growth in P is I think pretty okay. It looked pretty reasonable. One question I have is, have you thought about doing something else in DG? Have you thought about CG, continuous Galerkin, so H1, H curl, methods like that?
Not really, because we were really interested on the DG side, and we saw that this is just a subcase. Actually, your work in your paper for subcubes.
Yep.
We are really interested in the DG, so
Yep.
we didn't think about to do it for continuous Galerkin.
Yeah.
At this moment, for simplices.
Yeah. Nice idea. I like the dual mesh.
Thank you. Actually, it really resembles what you were doing for subcubes.
Yep.
But in a different manner.
Yeah. So you mentioned briefly that there's some GPU implementations. Can you talk about your experience with GPUs, in particular the performance of simplices on GPUs? Are you happy with where you are there for high orders, or?
So I have to say that now We have a prototype that is not running on GPUs, and we have a
Mhm.
demonstrator that is going to be ready for GPUs, but we didn't do the analysis. This is something that Josep de la Puente is pushing.
Mhm.
And my experience with GPUs, with simplices, goes to between 2009 and 2011, when this CUDA thing appeared. Okay, and actually what I was doing there, it was a sparse matrix vector product for HDG, specific purpose.
Mhm.
So uh, I cannot tell you anything for the electromagnetics course because we don't have
Oh,
ready yet the solver. But of course, what we are going to expect is that the sum factorization that you have for cubes, it's going to be a big difference with simplices because you cannot do that if you want symmetric points. Of course, if you want chirality in your nodal points, you can do that. You can do some factorization,
yeah.
but we are going to see differences because of this sum factorization thing. I guess you think something similar.
Yes. Yes. Yeah. There's a penalty for the same number of elements, but for the same mesh size. Sorry, but that's kind of expected.
Yeah.
All right. Any additional questions for Chevy? This is your chance.
And while someone thinks if he wants to make a question or not, or she, uh, I want to say something about this simplices and cubes thing. Okay.
Mhm.
And it's true that the solver is going to be slower, but it's also true that the time to do the mesh sometimes it's more than.
Yes.
And this is something that sometimes we all of us forget. And this is something that with Aloy we say a lot, no? The time that we spend cleaning CADs and doing the linear mesh is a lot compared to the time that you are actually running the simulation on the supercomputer, no?
I agree.
And I'm not saying that it's not important to get performance. And of course, if I could do simplices as fast as Zeta, that would be incredible. But that's not the case. But it's true that sometimes we spend more time preparing the CADs and cleaning and doing the linear mesh than actually running the simulation.
Yeah, I think it really also matters a lot of how complex the meshing is. There are areas where the meshing is not that complex. But in
I
engineering
agree.
applications, it often is. And then that's the weight. That has a huge weight on the overall cost. Yeah, I agree with that.